So now we're looking at thermodynamics, and thermodynamics is, as its name implies, taking thermal energy and converting that into motion. So thermo, heat, dynamics, motion is basically the idea behind the Industrial Revolution, where they were able to take different types of fuels, such as coal, to power steam engines and use them to do work. So there are three laws of thermodynamics that we come across, and these are all developed about the time that steam engines were being studied, and we're trying to get a better idea of how to make better steam engines. And the first law of thermodynamics is actually a restatement of the conservation of energy law. It states that the change in internal energy of a system, so we can think of the internal energy as being related to the energy, the thermal energy related to the temperature, the average microscopic kinetic energy, and also the bonding energy between different molecules and whatnot. But that thermal energy can change either by bringing heat in, okay, or having heat go out. So you can't create or destroy energy, it must come from someplace. Additionally, we are going to want our system to do work. So work that our system does will also come at the expense of its internal energy. So again, the first law of thermodynamics, and it's written a number of different ways. Usually we say that internal energy is delta U. I'm sorry, I should say internal energy is U. So we would say that the change in internal energy is equal to Q, the heat added. If we're adding heat, Q is positive. If we're taking away heat, Q is negative, minus the work done. So just conservation of energy, nothing all that complicated. What is a heat engine? Well, a heat engine is something that takes thermal energy in the form of heat, converts some of it into work, but this comes at a price, okay? Not all the work can be converted, not all the heat can be converted into 100% work. So some of the heat actually has to be dumped back into the environment where it is simply lost and is not useful in terms of doing anything. So again, we can think about a heat engine as taking some energy from a source. This can be a chemical source. It can be a source such as a nuclear reactor. Some form of energy is going to be converted into heat. Once it's converted into heat, typically we're going to allow some sort of gas, fluid, whatever, expand. And as it does so, it is going to do work. However, we've got to get rid of some of the heat that we've generated. So what we need to do is dump that heat as waste into the environment. And of course, we can see factories have smokestacks, internal combustion engines have exhausts. All of these are a way of not only getting the reaction products into the environment, but also dumping waste heat. So that's our general idea here. We're not going to be able to get all of it. We're going to try to get as much of the heat as possible to do work for us. One of the easiest ways to do work, and one of the first ways that people realized how to do work on the environment, was to use something called a cylinder. And a cylinder would be this cylindrical container, which would have this movable piston. And every time that the piston moved forward, the piston could do work. We could take that energy. We know, of course, that work is equal to force, okay? How much force can this piston produce on the environment, times distance, how far the piston would move forward. Okay, so how are we going to make that piston move? Well, that's not that hard. Think about it. Anytime we heat a gas, that gas increases in pressure. It wants to occupy more volume. So there's going to be more force on the piston, so it can do more force and do work on the outside. So that was basically the idea of some of the first steam engines. You heat up, typically water. The water produces steam. The steam then goes into a piston. The piston moves forward, and a lot of times they want reciprocal motion. They want cyclical motion, so they have the piston hooked up to a flywheel. The flywheel would turn, and that's where they'd get their work from. The problem is the piston can't move forward forever. So what we need to do is either cool the hot gas down, okay, so it has less pressure and it wants to contract, or if we want to get rid of this hot gas completely, we simply vent it into the environment. So the steam engine would have steam enter the gas cylinder. The cylinder would expand, it would do work on the environment. And then on the next phase, we would compress the cylinder, basically just have the steam go to the outside. And this would allow the whole process to begin over again. The problem is when you recompress the cylinder, you are doing work. So we always lose a little bit of energy as we dump the heat to the outside. And again, we can see this in our diagram before. Once again, what is our idea here? Well, we want to get as much work out of the system as possible, okay? So we use the heat to do work on the outside. But when we recompress the piston, we need to get rid of all that hot material that we have already. So we dump that heat into the environment as we recompress the cylinder, and we exhaust out this energy that we've already, or this heat that we've already used, this hot gas that we've already used. So basically, putting together an engine cycle, okay? Putting together a process that is going to lead to getting work out of the system generally involves allowing a hot gas to expand, okay, and do work on the outside, and let a cold gas be compressed to allow the piston to reset, okay? And of course, this will repeat itself over and over again. So let's look at the steam engine. Once again, what was happening with the steam engine? Really the first heat engine that was practical. Well, we had some hot reservoir, something we call a boiler, which we would generally just take this hot flame, usually burning coal, okay, back during the Industrial Revolution, and that would convert the chemical energy from the coal into latent energy or latent heat from the steam, and then that steam would be sent to a cylinder where it would be allowed to expand and do work, okay? Once it had expanded, the steam would then be pushed out of the system and dumped out of the environment. Now, believe it or not, the first steam engine was not developed by any famous scientist. It was actually developed by a blacksmith by the name of Thomas Newcomen, who was just very good with working with materials. What he did was create the basis for a heat engine. He created a boiler, which he would power with coal. And the idea here was to basically develop this engine that could mechanically remove water from a coal mine. And before, you'd have to use a hand pump, or you'd have to use livestock to power this little piston pump that would extract water. Now, the problem with this is it was very, very inefficient. At the time, Newcomen was trying to solve a basic problem of mining, which was as you dug deeper and deeper into the earth, you eventually reached the water table. When you hit the water table, unless you were able to remove that water, you weren't going any further. And what this meant is that many mines had to be abandoned, or many quarries had to be abandoned as they filled up with water. Well, with Newcomen's engine, he could pump out the water as it would seep into the mine. And he could do this again by burning coal, but it wasn't very efficient. Okay. You had to burn a lot of coal to move a little bit of water. James Watt, however, figured out that if you could make the compression cycle lose less energy, he did this in 1763, you could greatly improve the efficiency of the engine. And he developed this idea of a separate steam condenser system about the time that he was working on a Newcomen engine. And this dramatically increased the efficiency of the engine. So we named not the unit of power after Newcomen, but rather after Watt, who improved Newcomen's engine. So again, we think about steam engines, and it's very, very simple. We use chemical energy to produce heat. This produces steam. The steam does work on the cylinder. The cylinder can do work on the outside. And then that steam is recondensed and then dumped to the outside. Now, steam engines were really responsible for the second industrial revolution. Of course, there are great strides that were made in agriculture too, but it was really this availability of inexpensive work, mechanical work, that powered industry. The problem with this is steam engines, when they were first built, were built out of relatively inferior materials. The materials that were used were primarily iron, wrought iron, mild steel would probably be the best material available, but really in very low quantities. What this meant is that with many of the designs of the steam engines, they would lead to very tragic accidents. It's actually a picture of a steam locomotive that blew up due to the flash explosion of steam. And we can see how a lot of these steam engines were produced. Instead of just having one big boiler, what they would do is they'd have water go through these heat exchanger pipes. And the flames of whatever you were burning would basically heat these pipes and transfer the energy from the chemical reaction to the steam itself. The problem is the water, which would be used to generate the steam, would be surrounding these pipes. And as it was heated, the water would turn into steam. But for moving things like locomotives and steamships, the water would end up sloshing forward and backward inside these enclosures. And that would mean that there'd be some points where the water wouldn't be present to cool down the pipes, and the pipes would get very, very hot. Well, when the water would return back to that location where the pipes had become very hot, it would flash boil, it would instantly turn into steam. There'd be a huge jump in pressure, and that would lead to the boiler to basically exploding. And this, of course, resulted in many tragic events. What we see right here is the result of a steam locomotive exploding. But in the case of steam ships, where the boilers were much larger, you would get, not only would the entire ship be compromised and perhaps destroyed, but the release of steam would create horrific injuries to not only those working in the steam engine, in the engine room, but also to the people who are being transported. There was an incident during the Civil War where in heavy seas, the sloshing back and forth of water led to one of these flash steam explosions, and it killed over 100 Union troops who were returning from the fight. So again, an incredibly important invention as far as the Industrial Revolution goes. But of course, like any technology, when it's first employed, it was a very dangerous technology until better materials and better designs were used. One way to improve safety was an attempt to improve the efficiency of the engine, so you didn't need as much energy in them to do the same amount of work. And Nicolas Léonard Sadi-Carnot was a French physicist who worked on improving the steam engine to, again, decrease the amount of energy that was being generated and make them as efficient as possible. And what he discovered is that if you allow a cylinder to expand at a constant temperature and then expand freely and then compress at a constant temperature and compress freely in 4 different phases, known as a Carnot phase, you could get the most efficient engine possible, and again, reduce the need to have as much energy present. This was a theoretical engine. Practically, it was very difficult to implement. But Stirling looked at Carnot's engine cycle and discovered that he could produce a mechanical engine that would come very close to the Carnot cycle. And this is called the Stirling engine. But unfortunately, the Stirling engine, again, given the materials that were available, was too bulky and expensive to build at the time. So Moses steam engines remain less efficient and quite dangerous. What's interesting is now with the advent of new technology, Stirling engines have made a comeback. They were actually invented back in 1816 to improve, again, the safety and efficiency of steam engines. But now, due to their high efficiency, they're actually being used in cooperation with solar energy to produce electricity in a very different way than we envision most solar energy. Most solar energy, we think of photovoltaic cells. These cells that convert electrical energy into, solar energy into electrical energy. This Stirling engine solar collector actually can be more efficient than photoelectric cells. It takes the sunlight, concentrates it onto a heat exchanger. That heat exchanger is then connected to a small Stirling engine, and then that converts it from heat into electricity. And whereas most photovoltaic cells are below 20% efficient, this has been proven to be as high as 50% efficient. Now, the internal combustion engine is obviously a heat engine. It's different from the steam engine. If we think about the steam engine, once again, the steam engine had a hot reservoir, which was the boiler, had a cold reservoir, which was the outside, and of course, the piston was the engine itself. An internal combustion engine doesn't have an external boiler. As its name implies, the combustion takes place not in a separate chamber, but within the cylinder itself. Again, think about the steam engine. We have an external heat source. You're heating the boiler, usually from underneath, using the flames from some chemical reaction, burning coal, burning oil, burning whatever, okay? Then that heat is transferred to the boiler, which becomes your hot reservoir, produces steam, and the steam goes into the piston. Here, we take a mixture of gasoline and air, we compress it, light a spark, okay, from a spark plug, that ignites the gas. The gas becomes very hot, produces a lot of pressure, pushes down on the cylinder, and then the exhaust is driven out of the cylinder. Now we call this a 4-cycle engine because there's 4 phases to what goes on here. The first phase is we draw in the air and the fuel. The next phase is we undergo compression. We undergo combustion, and then after the combustion has pushed the cylinder down, the cylinder pushes the exhaust out. So that is a 4-cycle engine. In a 2-cycle engine, we actually combine the exhaust and the compression at the same time. So they're less efficient and much more pollutive, those types of engines. Now, internal combustion engines are generally not that efficient. Older engines probably got about 20% efficiency. Newer engines at best maybe get about 30% efficiency. That means that 70 to 80% of all the energy that you use simply goes into waste heat. To improve this, according to Carnot's study in his cycle, Carnot found out that the efficiency of a gas engine, or any engine, increases as we make the cold temperature colder. Well, it can't make the cold temperature any colder, that's the outside, and make the hot temperature hotter, which for an internal combustion engine, that makes the cylinder combustion temperature higher. Now, the problem with that is the higher we make the internal temperature, the more heat we place on the cylinder parts and the more wear and tear they experience. That means that an engine running hotter is more efficient, but an engine running hotter is also going to wear out faster. So what we do is we actually experiment with other materials. We experiment with tougher alloys. We coat alloys with ceramics, which are very good at standing up to heat. But again, this improves the cost of the engines. And that's why the auto industry, you know, when they talk about making engines more efficient, they're against it because it really cuts into their costs. There comes a point where you can only get so much efficiency before the cost becomes unmanageable. So again, in engineering these internal combustion engines, there's a real challenge. We want to keep the costs low. We want to keep the durability high, the reliability high, but we also want to keep them as efficient as possible. So high efficiency, lower cost, higher durability. These are challenges that they have to balance. Diesel engines are more efficient than gasoline engines because they're higher compression ratios, but diesels have a number of problems. One, they're much more expensive, they weigh more, they're noisier, okay, and they produce more pollution. We have improved their technology where newer diesel engines are becoming much less pollutant. In fact, today's diesel engines, you actually have to add a fluid to the exhaust system, where the fluid will actually capture a lot of the emissions that are given off. But in any case, diesel engines do provide greater efficiency. Power plants are also heat engines. Again, if we look at today's power plants, they're very, very similar to even the original steam engines. There's an energy source, either it's some chemical energies that are being burned, coal, oil, or natural gas. Or in the case of nuclear power, there's a reactor that's going to heat up the steam. But in any case, both systems start with a steam generator, some type of boiler. For the nuclear power plant, it is called a steam generator. For a fossil fuel power plant, it's called a boiler. They both generate steam. The steam is sent through turbines. Turbines are more efficient than cylinders. Like a turbine, it allows the steam to expand and do work. As the steam expands, it turns a turbine, and then that work is done on a generator, which generates electricity. Once the steam is passed through the turbine and given up a large amount of its energy, we get rid of even more energy by condensing it, okay? The famous cooling towers, the hyperbolic cooling towers that you'll sometimes, oops, try to switch the pen here, that you'll sometimes see near nuclear reactors, actually are made to recondense the steam. And the way that they work is the water will actually flow on the inside walls of these towers. And the water will start at the top. It's hot water. As it does so, it goes down the sides. And believe it or not, these things are not filled with water. They're actually filled with air. They're hollow. And cool air will enter at the bottom of these cooling towers, go upward, and through evaporation will cool the hot water as it flows down the sides of the cooling towers. Again, we see these mainly at nuclear power plants, but they're actually at some fossil fuel power plants too. And what they're trying to do is, again, cool off the steam which has been generated by the boilers, okay? Again, usually there's a second system here. The water that goes to the cooling towers is usually this light blue that you see in the condensers. And usually that's either sent to a cooling tower, okay? You can send it to an evaporator. I don't know if many of you go on the turnpike, but there's two power stations. There's one right on the exit, right near the exit to 15E, and there's another one near the exit of 16W. And both of them use evaporators. Or you can just use a large body of water. Many power plants are located near either the ocean, they're located near a river, and they can dump a lot of the waste energy there. But again, basic heat engine. Heat comes from some source, we use it to do work, and we dump the waste heat into the environment. Jet engines are also heat engines. Instead of the cycle being broken down into different phases, as it is for the internal combustion engine, a jet engine will do it continuously. Okay, that's what we saw for the power plant. It's continuously generating power. There's steam production, there's work being done by the steam, there's steam being condensed back into water, and then again, it's reheated right here, okay? So it's being done continuously throughout the power plant. For jet engine, it's pretty much the same thing, okay? We have combustion, which is taking place in these combustion chambers right here, where the gas is combined with fuel. I should say air is combined with fuel, okay? Air is being drawn in through these compressor blades. It's being compressed, combined with fuel. The fuel-air mixture is ignited, okay? Once the jet engine is going, it becomes very, very hot and instantaneously ignites from the compression, from the high heat. And then that expanding gas does work on this back turbine right here, which turns the compressor blades, okay? And basically, if we see what's going on here, work equals force times distance, there's work done on the turbine blades, but there's also work done on the air being pushed backward, and this propels the plane forward. So definitely a heat engine. Again, efficiency is something that's very, very important to engines. Efficiency is how much work we get from the engine compared to how much energy we put into that, okay? And we can never reach 100% efficiency, okay? We always have to get rid of some of the energy as waste heat. However, Carnot's study of the thermodynamic cycle tells us again that even though no real engine operating between two energy reserves can be more efficient than the Carnot engine, the Carnot cycle represents the best efficiency we can get given two different temperatures. And again, the whole push to make engines more and more efficient is to get this efficiency closer and closer to 1. Really, the other way that we can write this equation is times 100%. You know, if we write in percentiles, we want to get as close to 100% as possible, okay? If we could make the cold reservoir absolute zero, or we can make the hot reservoir infinity, we could have a 100% efficient engine. Of course, that's impossible. So the best that we can hope for in any of these systems is to make TH as large as possible. The bigger TH becomes, the higher we can make that right there, the bigger we make this denominator. The larger this denominator becomes, the less energy we subtract, or the less efficiency we subtract, and the closer to 1 that we get. Let me give you an example. In this equation, we've got to put everything in Kelvin. Let's look at the efficiency, okay? For the case where an engine operates at 500 degrees Kelvin, okay? 500 degrees, by the way, would be roughly, I don't know, about 250 degrees Celsius. Again, I'm saying roughly, it's more like 230 degrees Celsius. Not that hot of a temperature, but well above the temperature that water boils, okay? So I'm going to put 500 here. And let's say that the outside environment's about 300 degrees Kelvin here. Okay. I did it backwards. Let's go backwards. Okay, 1 minus, here's my mistake. The outside temperature is almost always 300 degrees Kelvin. So our cold reservoir is almost always 300. Now I'm going to divide this by 500, my hot reservoir, okay? And if I do this, 3 divided by 5 is 0.6. That gives me 1 minus 0.6, okay? And that is 0.4, or 40% efficiency, okay? That means, again, 60% of the energy is going to be lost to the environment, okay? Now watch what happens when I take the 500, okay, so I'm going to reset this right here, and I double the temperature. Now I increase the temperature to 1,000 degrees Kelvin. Now I'm subtracting 3 divided by 10 is 0.3. That's 0.07, or 70%. By doubling the temperature of the heat engine, I've gone from 40% to 70%. So you can see why there's such a push to increase the performance of some of these internal combustion engines by raising the internal temperature. Even a small temperature change has a profound effect on the efficiency of the engine. Okay, let's go to the next one. The second law of thermodynamics. Remember I said there's 3. The second law of thermodynamics states that the entropy for a closed system must increase with time. Whoa, what does that mean? What is this entropy? All right, now we get into some pretty abstract things. Entropy is a measured disorder. We can think of entropy as being a measure of how difficult it is to turn energy into useful work. As the entropy of a system increases, the amount of useful work available becomes less and less. Okay? So entropy is a very important way of trying to figure out whether or not a system is going to be efficient or it's not going to be very efficient. The less you change the entropy for a given heat engine, the more efficient it's going to become. Okay, good example of entropy. You've seen these dominoes, right? You set up all these dominoes. Entropy of this system will naturally want to go where all the dominoes will fall, okay? So spontaneously, if I start this process, each domino after the next is going to knock down its neighbor. So suddenly, all the dominoes are knocked over. That's an increase in entropy. Okay? But what will not happen is the dominoes naturally setting themselves back up. Somebody else has to do that. So in this system, we see entropy naturally increases, and there's less energy available to do work, in this case, for the dominoes to fall. The second law of thermodynamics, again, talks about entropy. But what happens as a result is that no engine can be designed such that 100% of all the energy is converted into work. Okay? That can't happen. A small amount of energy always has to be dumped into the cold reservoir. So a consequence of the second law is that no energy can be 100% efficient. Okay? Let's talk about something else, heat pumps. A heat engine takes energy from the hot reservoir, sends it through a heat engine, turns some of that into work, and dumps the excess energy to cold reservoir. Okay? It's sort of like the way water flows over a water wheel. Okay? Water flows from up the river, goes down the river, and we can put turbines in its way, and we can generate hydroelectric energy from that. We can do work from that. Okay? So water naturally likes to flow from a higher temperature to a colder temperature. Okay? But what if we want the heat to go the other way? What if we want heat to go from a colder area and dump it into a warmer area? Is that possible? Well, it is, but it's going to take work. All right? We're going to have to expend energy to pump the water uphill. Okay? In this case, we're pumping heat uphill. Yes, heat's not a substance. Heat is energy. But the analogy of water is a very important one here. If we let heat to its own devices, heat will just go from a higher temperature to a lower temperature. If we, however, use work, we can move the heat from a colder temperature, just like moving water from a lower elevation to a higher elevation, simply using some of the processes of thermodynamics. Okay. Where do we want to do this? Why would we want to do this? Well, the applications for a heat pump are very important. Your freezer pumps cold, well, it doesn't pump cold air. It takes the heat from the interior and pumps it to the exterior, as does your refrigerator, to keep your food cold. All right, so it extracts energy from the inside. The freezer, the refrigerator, they're insulated. So it makes it very difficult for heat to get in. So once it's insulated, you can now extract this heat through a heat pump and dump it to the outside. Air conditioners, same thing. You want to take the interior house, your apartment, whatever, your dorm, you want to cool it down. How do you do that? You got to take the heat that's inside and somehow get it outside. So think about the cold reservoir being a little bit different in this case. In this case, your cold reservoir is actually the region that you want to make cold. Okay. We extract heat from it, we put it into the heat pump. The heat pump will then dump it outside where the temperature is higher. Now, because heat doesn't naturally like to flow from cold to hot, we have to play a few games right here, okay? We have to play some games right here, and we're going to use work to do this. We're going to use a refrigerant, and we're going to compress and expand the refrigerant gas, or the refrigerant, so that it can change temperature and absorb heat from the cold reservoir. Okay, we're going to cool down the refrigerant, make it cold so it absorbs heat from the cold reservoir. And then we're going to compress it, which heats it up, and that is going to allow it to become warm on the outside, and then it can dump heat to the outside. So here's a heat pump system. Again, we have some region that we want to make cold. We want to make this interior cold, okay? Refrigerator, freezer, air conditioner, whatever. We want to remove heat from it, okay? So we use the refrigerant to extract heat from it, okay? Refrigerant is cold once again, and then heat the refrigerant up so it naturally wants to dump the heat into the environment. But again, this will come at a cost. This doesn't happen naturally. We need to do work on the gas, the refrigerant, to make it hot sometimes and make it cold other times. I like to say that this is sort of like analogous to a sponge. When you compress a sponge, you force the water out. When you relax a sponge and allow it to expand, it can absorb water. Same thing with this refrigerant. When we compress it, it becomes hot and it tends to give off the heat. When we expand it, it tends to become cold, okay, through a process we call adiabatic expansion. All right. So let's see how this is set up. How is this refrigerator set up? Well, normally you can have a less expensive system where the one system will cool down the refrigerator and the freezer. But in most cases, there's going to be a separate refrigerant system on the back of this for the freezer and a separate one for the refrigerator. Most refrigerators, if you go to the back of them, you'll actually feel that they're warm because the heat exchanger back there is dumping that heat from the inside to the outside. Okay, what does the refrigerant system look like? Well, here is actually a heat pump system. And what we see here is this is the back heat exchanger. This is where all the heat's going to be dumped into the environment. Okay, blows air through here. Okay, and that dumps the heat to the outside, okay? On the other side, what you can't see is a heat exchanger that's connected to the interior of the freezer or refrigerator. That is going to basically absorb heat from the interior there and then dump it to the outside. All right. What can we see here? Not quite certain that we can see everything here. The motor, I think the motor you can't see. In any case, let's take a look at a diagram of this. Here is our heat pump in its simplest form, okay? On this side, we have the electric motor. This is where the work is going to be done. So the work goes in here, okay? Typically, the work comes from electrical energy. That electrical energy is turned into mechanical energy. And that's basically going to power the whole system or pump the heat from the cold reservoir to the hot reservoir. Remember, right down here is where you have all your food. This is your refrigerator. This is your freezer. If it's an air conditioner, this is the interior of your house. This is your cold reservoir. Okay? So, first thing that happens right here. The refrigerant, okay, and it used to be chlorofluorocarbons, by the way. Now they're using other fluorocarbons that don't damage the ozone layer. But the fluorocarbons come from the cold region. They're put into the pump, so they generally start out somewhat cool, okay? Not cold, but cool because they've absorbed some of the heat. The compression pump is going to compress the gas through a process we call adiabatic compression. Now, adiabatic compression, when I do work on a gas, that energy, that internal energy has to go someplace. So all of a sudden, refrigerant becomes very, very hot, okay? It's under high pressure and it's very, very hot. It's circulated here where it begins to release its energy. Now, even though the environment's warmer than inside of the refrigerator or the air conditioner, okay, the refrigerant has become so hot that its temperature is maybe 150 degrees Fahrenheit or even 200 degrees Fahrenheit. It's really at a much higher temperature than the surroundings. So the heat's going to go, yeah, I want to go from hot to cold. The refrigerant right now is hot. So I'm going to dump it into the outside environment. Okay? So now our refrigerant is still warm, okay? Still pretty hot, but we're going to say, oops, undo that. We're going to say that it's warm. When we say warm, it's at least the temperature of the outside environment, so it's probably, over 100 degrees, okay? But now it goes through something called a needle valve where it's going to rapidly expand. When you take a gas and you rapidly expand it, it will drop in temperature. Basically, it does work on the environment, and that means it's got to give up energy, so it gives up thermal energy. Spray an aerosol can sometime and notice how the temperature drops. In this needle valve, we go from a very high pressure to a much lower pressure, and now the refrigerant becomes cold. Okay? So what's going to happen now? Its temperature is probably well below 0 on the Fahrenheit scale. So all the heat within your refrigerator or freezer, or the heat from the room in your air conditioner, all of that's going to flow into this much cooler heat exchanger, okay? Where even if it's a freezer, you want it about 0 degrees Fahrenheit, okay? Now the refrigerant is probably -20, -40 degrees Fahrenheit. And that's how it's able to cool. Now, the reason why we use chlorofluorocarbons is because there are only certain refrigerants which go through phase changes about the temperature that heat pumps operate. So chlorofluorocarbons were used to replace ammonia, which could be dangerous. It could cause explosions because ammonia was really the first refrigerant used in these types of systems. They went to the chlorofluorocarbons thinking that they're completely safe until we started seeing the ozone layer disappearing, especially in the polar regions. So now we've gone from chlorofluorocarbons to other fluorocarbons, which are not damaging. But again, heat pump, that's how we pump heat out of a cold area and dump it to a warm area. Heat pumps are rated according to their performance. If they're in the refrigerator, they're always pumping heat from the interior of the refrigerator outward. If they're in their freezer, same thing, from the inside to the outside. If, however, we're using it to both heat and cool a home, we can actually reverse this process, okay? With the heat pump, if we're in our cooling mode, which is basically when it's acting like an air conditioner, we say the coefficient of performance is how much heat can we remove from the cold reservoir, which would be the interior of our house, and dump it to the outside given the amount of work that we do. Now, surprisingly, this coefficient of performance can be greater than 1. This is not efficiency, okay? This is saying how many joules of heat can I remove given I have this many joules of electrical energy coming in. All right, so if I'm reaching a coefficient of performance of 5, that means that if I want to remove, for instance, it's not a lot of heat, by the way. Let's say I want to remove 500 joules of heat from my house using this heat pump, I would only need 100 joules of electricity to do so, okay? So this shows, basically how a heat pump can perform. And generally, the coefficient of performance goes down as it gets hotter and hotter outside, okay? If it's a cool day, your air conditioner doesn't have to work too hard because it's not having to move very much heat, and it's not having to move it against a very high temperature. As the temperature becomes greater and greater outside, just like pumping a liquid to a higher and higher elevation, if you're pumping this heat against a higher and higher temperature, the coefficient of performance is going to go down. But the great thing about these heat pumps is you can actually reverse them, okay? Now, and again, this shows the energy flow in a heat pump. You can extract heat from other sources, maybe the earth, extract the heat from the earth and use the heat pump to then pump it inside your home, okay? Now, the great thing is that the earth is always around 50 degrees Fahrenheit, okay? Remains about that constant all year round, all right? Now, what that means is it would take almost no energy to keep your house at 50 degrees Fahrenheit, but we obviously want to go much higher than that, maybe keep the house somewhere around 65 degrees Fahrenheit, okay? Well, it doesn't take very much energy to get that energy from the ground into our home. Just give it a little extra push with this work, and that's how we can heat our home. Now, here the coefficient of performance, typically isn't that high for very, very cold days. It also depends on where you're pumping your heat from. Some heat pumps can actually pump directly from the outside, but especially on a cold day, you're not going to get a very high coefficient of performance. If you're getting it from the ground, your coefficient of performance goes up significantly. So again, coefficient of performance, how much heat do I get into the house for the amount of electricity I have to spend? Any time that my coefficient of performance is greater than 1, I'm doing better than an electric heater, okay? Because an electric heater basically converts all of the electrical energy, okay, converts all the electrical energy into heat, okay? Here, the electrical energy is turned into work. It's nearly 100% efficient, okay? And that's much less than the heat that I actually move. So heat pumps are more efficient than electric heaters. And again, we're getting, usually with geothermal heat pumps, we're getting our heat directly from the ground. Heat pumps that use the outside air, again, they're going to be less efficient. So in the summertime, I want to cool my building. So what do? I dump the heat from inside the building, I dump it into the ground. And again, if the ground's 50 degrees Fahrenheit, and I want to cool my building to maybe 70 degrees Fahrenheit, okay? Heat naturally likes to go from warm to cold. That's not going to be a hard thing to do. In the wintertime again, colder outside. We want it to be warmer inside. It's going to take a little more energy to heat. But again, geothermal heat pumps, even though they use electricity, we generally think of electricity as being very inefficient to cool and heat. Heat pumps with their higher coefficient of performance far outperform most other means of heating and cooling. The big problem is it's the cost of putting in the ground system. If you're either digging wells for the heat exchanger in the ground or you're burying pipe, that initial cost can be very, very high. And here's some different coefficient of performances and how they're rated. Here's coefficient of performance as a function of the temperature. Unfortunately, this is from is it a Danish website? Well, in any case, so what you see as a comma is actually a decimal place. But you can see when it's warmer out, the coefficient of performance is over 6. As it gets colder out, the coefficient of performance gets worse and worse. But again, even in the coldest temperatures, it doesn't drop below 2. Let's talk about the last law of thermodynamics, the third law of thermodynamics. This is where we end. The third law of thermodynamics is concerned with entropy and absolute zero. This is probably the most abstract, okay? Let's just review. The first law was about conservation of energy. Okay, energy can't be created or destroyed. The internal heat or internal energy of a system is equal to the heat added minus the work done. Very straightforward. The second law concerned entropy, but we could use it to talk about efficiency, okay? That no heat pump, no heat engine could ever be 100% efficient. The third law is sort of a stop sign for us. It says the third law states that the entropy of a system goes to 0 as the temperature goes to 0. What it basically means is that all the processes that we would use to get down to absolute 0, okay? All the processes that we would use would require an infinite amount of energy. And therefore, even though we can get close to absolute 0, we can never reach absolute 0, okay? You can get, and I believe they've gotten 2 trillionths of a degree Kelvin, okay? But again, absolute 0 can never be achieved because as we get closer and closer, I think they call it Zeno's law, as you get closer, it takes more energy to do so. I'll give you an example, okay? Let's say that we are at, let me break this up. Let me do that again. Break it up in thirds, okay? Here's absolute 0, 0 degrees Kelvin. Okay, here's 100 degrees Kelvin. Here's 200 degrees Kelvin, okay? Here is 300 degrees Kelvin, which is close to room temperature on a really hot day. All right. If I'm using a system to cool down to that temperature, all right, I will use 1 full unit of energy to get halfway to absolute 0, okay? Maybe that's 1,000 joules, maybe that's whatever, okay? Just come up with an arbitrary number, put it there. To get down halfway closer, I'm halfway there, so I'm going to get down to a quarter of the distance. It'll take that same amount of energy, okay? Now to go to the next half, down to 1/8, it'll take the same amount of energy. And what happens is I keep spending the same amount of energy to go smaller and smaller distances. And even though I'm getting closer and closer, I will never reach absolute zero, no matter how much energy I expend. So what this means is there's not enough energy in the universe to get down to that 0 degrees Kelvin. And that's the basis for the third law of thermodynamics, that we can cool things very cold, but never quite get there. Okay.